I wanna be an engineer, so freaking bad. Optimize the things I've always...
No Tools Left Behind is a project that looks to address the problem of tools being left behind in surgery. These are termed RFOs, retained foreign objects. In America, 1 in every 1,000 to 1 in every 1,500 surgeries have an RFO, and sponges are the most common. In other regions such as Africa, 1 in every 677 surgeries have RFOs, and again, sponges are most common. So why are RFOs bad? Well, first of all, they cause infection. And furthermore, if you have an infection, you have to have more surgeries. This also leads to possible deaths. And moreover, on the economic side, it's about an $11 billion cost annually. So current technologies that are prevalent right now are the manual counting method, which is what most hospitals use right now. They use a 3 counting method where they count all of the sponges before the surgery, they count it before they're going to close up the surgery, and they count it again after the surgery is done. A new system that we're trying to compete with is the RFID tagging system. This system uses a radio frequency ID tag and a bulky computer system in which you can find the sponge that is tagged with the radio frequency. This system is expensive, and also it's not as affordable as other developing regions. Our original idea was to go with biodegradable sponge, but we were set back because of the cost of the polymers that we thought would be sufficient for the sponge, and so we had to come up with a new idea. Our current solution is to have a magnetically detectable sponge. Well, how is this more effective? First of all, it's significantly cheaper than the RFID system. An RFID system costs about $2,000 to $3,000 on just the computer, not to mention the additional cost of the RFID tag sponges. Also, our system uses less equipment. All we have is a sponge that's magnetically tagged and a Gauss meter which can detect a magnetic field. And also, we also want to mention that training is very minimal. For the RFID system, you need to have the nurses and the surgeons know how to use the computer, and so for our system, all you need is to know that if the sponge is being detected or not. Our design is to take a magnet and make a pocket within the sponge and place it in there.
This is the output of your preamplifier right here.
Wait, which one?
This right here.
Right here.
So you have to add a BNC or some kind of jack. I would recommend getting one of those little phono jacks, a mono jack. Go to Fry's, get one of the little mono ones. Figure out which pins the center and the outside are, and use that.
This is a circuit we made to boost the signal from our EMF meter. Here we start out with a 2-stage inverting instrumentation amplifier with a differential gain. And then this goes into 2 quad comparators. These act like voltage switches. If the voltage is high, then it's on, and then if it's low, then it's off. And lastly, these go into a transistor driver. This is basically used to power the LEDs.
Our adjusted magnetometer looks to overcome the slow sampling rate and can be seen through the LEDs. When a magnet is detected, the positive or negative fields will be displayed by the red or green LEDs. The red LEDs light up when a positive field is detected, and the green LEDs light up when a negative field is detected. Also, you can see that we have to adjust the magnetometer based on the orientation of the sensor. Once this adjustment has been made, the magnetometer is now ready to be used.
So we wanted to address this problem from like a practical standpoint. So the issue right now that we were trying to address is the distance away. Because obviously if the magnetic field isn't strong enough to go a certain distance, then it won't be detectable. So what we did is we did some calculations, we did some functions, put them into MATLAB, and then we wanted to see the magnetic field strength as a function of distance. So as distance increases, your magnetic field goes down. And then we wanted to actually do this experiment. iPhones actually have a magnetometer built in that we can use. So we use a magnetometer and we tested we bought some magnets, we tested them at different distances to see if we could detect them.
Oh, every time I close my eyes, I calculate a new design, yeah, an efficient way to quantify, oh, I swear.
We actually want to do a demonstration for you guys. So, Dr. Kai, do you mind being an assistant?
It's payback time, huh?
Okay, so basically what we're going to do is we're going to use...
Open me up and put magnets in me?
So here we have the magnetometer here, and we're going to hold our hands out. We want you to detect the magnet.
So one of them has magnet, one of them doesn't.
So we're going to, all of us will open our hands up. Come over here, guys. And I want you to find the magnet.
Magnetic. Got something in that hand.
Alright, so which hand do you think it is? Right? Yeah. So just to show you guys, this is the magnet that was detected,
And it's really small. And the cost of these magnets is, currently we only bought 10 of them, and so the price is relatively expensive compared to bulk prices. This one costs about 50 cents, but on the range, if you buy it in bulk, the prices can go down up to 20 to 25 cents to 30, or in 25 to 30 range. So that's about how much these.
and even more with that, Dr. Klein had no prior training as so you can imagine, like with an RFID, that demonstration would not have been possible. Depending on the geometry of the magnet, you have a different equation for the magnetic field. And here's the MATLAB computations that we did. So just so the audience isn't confused, this is not going to 0 Gauss as it seems on the thing. It's just a smaller amount. So you can see how the magnetic field kind of decreases, and different geometries have their strengths. But so we set an arbitrary distance that we want to be able to detect. So we set that arbitrary distance to be about 6 inches from now, and so that would be our goal for detection. So we evaluated the functions at a distance of 6 inches, and then we saw the magnetic strength. So you can see they're on the order of like the best magnet that we have is the D36, which is a cylindrical magnet, and it's 0.1 Gauss. So we need a detector that can detect in that range. So this is the detector we're ultimately we haven't got a detector yet, but this is the detector we're going to find. So here's the actual test that we use with the iPhone. So you can see that the bigger magnets can be detected farther away, and the smaller magnets obviously have less strength. And just to clarify, the baseline reading for the iPhone magnetometer is about 40 microtesla because of the Earth's residual magnetic field. So anything above 40 can be detected. So obviously the smaller cube magnet in this diagram and the smaller cylindrical magnet cannot be detected from 4 inches with the iPhone magnetometer. But again, the iPhone magnetometer is a simple magnetometer. It's not meant to detect small magnetic fields. It's maybe on the range of like 1 microtesla. And just to put that in perspective, 1 Tesla is 1 times 10 to the negative 6 Tesla is 10 Gauss.
The first and most important clearance that must be achieved through the FDA is a Class 1 510K clearance.
The 510K clearance is simply a clearance that states that the product is equivalent to another product out in the market already.
As labeling a product functions is extremely important, there must be a 21 CFR Part 801 clearance to make sure that the product labels are consistent, descriptive, and informative of the functions of the device.
If there is electronic radiation found in our product, we must meet the electronic product radiation control provision that can be found in 21 CFR 101050. Over the course of the year, we've learned many valuable lessons. For one, we realized that brainstorming and researching ideas is crucial when designing a solution for any given problem. We've brainstormed and researched multiple ideas, and without that step in the process, we wouldn't have been able to create our solution, magnetically detectable sponges.
We learned how to be efficient within our group, work with peers, and have designed a product that may actually be used in hospitals.
So in conclusion, RFOs are a prevalent problem, a global health problem. The current solutions, RFID, they're very complicated, they're very expensive, and the problem with the MagnaCount system, it's cheap, but it's unreliable. And we think that our magnetically detect sponges will address this problem.
Wanna be an engineer so freaking bad.